Right. Welcome to the deep dive. Today we're going straight to the source material. We're
Yeah.
pulling insights directly from the presentation notes of a Nobel Prize winner to, get some instant clarity on a really technical breakthrough.
That's right. We're looking at excerpts from the 1998 Nobel Lecture given by Daniel C. Tsui for
For
physics.
physics, right. And the goal here is to really understand the achievement itself.
And the interesting thing is it's all captured really in the title of his lecture.
Okay, let's hear it.
Yeah.
It's a mouthful.
Yeah.
It's Interplay of Disorder and Interaction in Two-Dimensional Electron Gas in Intense Magnetic Fields.
Yeah.
So, where do we even start with that? That's a lot of jargon.
Well, I think we should probably start with the result. All of those technical terms, the electron gas, the magnetic fields, they all led to the observation of something called the fractional quantum Hall effect.
The FQHE.
The FQHE, exactly. That's the discovery.
So how does that very dense title actually explain what's going on?
It explains the very specific and kind of weird conditions. So first, you have the setup, two-dimensional electron gas.
Which basically means electrons are stuck on a flat plane, right?
Essentially, yes,
Yeah.
they're confined. Then you add intense magnetic fields, and you'd expect their behavior to be, very constrained, but also very predictable.
But it wasn't.
It was not.
And that's where the interplay of disorder and interaction comes in. I mean, to me, disorder sounds like noise, like an imperfection that would just ruin the whole experiment.
You would think so, and that is what is so fascinating here. The disorder, these tiny imperfections in the material, was actually necessary.
Necessary how?
It sort of allowed the interactions between the electrons to just take over, to dominate. It forced them into this bizarre new collective state.
So they're not acting like individual particles anymore.
Not at all. They organize themselves into what we call a quantum fluid. It moves with zero friction, and the electrons act like these new quasi-particles that have fractional charges. Yeah, it completely changed how we understood electronic behavior.
It's just amazing that something so fundamental, I mean, just confining electrons in a specific way, leads to a completely new form of matter.
It is.
And this unbelievably specific piece of physics, it falls under the big Nobel mandate, right?
Yeah.
That the prizes are for achievements that have conferred the greatest benefit to humankind.
Exactly. And the source context we have points that out. I mean, the awards cover everything from quantum tunneling all the way to promoting democratic rights. Tsui's work just shows how deep the roots of scientific benefit can go.
So let's just ground this in time for a second. We've defined the physics, but when did this become, foundational knowledge?
Well, the moment was really the lecture itself. It was December 8th, 1998. That was the day he delivered this talk, the formal presentation of this world-changing work to the scientific community.
So the big takeaway here is how incredibly focused, how specific the science that ultimately benefits all of us can actually be.
It is, and that really leaves a question for you, the learner, to consider. Given that this incredibly fundamental research was seen as a huge benefit to humanity, how do you think the abstract physics of a two-dimensional electron gas? How does that eventually translate into a tangible product or technology we might use every day?
That delayed impact of pure discovery.
Exactly. That's something for you to think about.